combined sewer is a sewage collection system of pipes and tunnels designed to also collect surface runoff. Combined sewers can cause serious water pollution problems during combined sewer overflow events when wet weather flows exceed the sewage treatment plant capacity. This type of sewer design is no longer used in building new communities, but many older cities continue to operate combined sewers. Background: most sewage collection systems of the 19th and early to mid-20th century used single pipe systems that collect both sewage and urban runoff from streets and roofs. This type of collection system is referred to as a combined sewer system. The rationale for combining the two was that it would be cheaper to build just a single system. Most cities at the time did not have sewage treatment plants, so there was no perceived public health advantage in constructing a separate surface water sewerage, or storm sewer system. When constructed, combined sewer systems were typically sized to carry 3 to 160 times the average dry weather sewage flows. It is generally infeasible to treat the volume of mixed sewage and surface runoff flowing in a combined sewer during peak runoff events caused by snowmelt or convective precipitation. As cities built sewage treatment plants, those plants were typically built to treat only the volume of sewage flowing during dry weather. Relief structures were installed in the collection system to bypass untreated sewage mixed with surface runoff during wet weather, protecting sewage treatment plants from damage caused if peak flows reached the headworks. Combined sewer overflows. These relief structures, called stormwater regulators, are constructed in combined sewer systems to divert flows in excess of the peak design flow of the sewage treatment plant. Combined sewers are built with control sections establishing stage discharge or pressure differential discharge relationships which may be either predicted or calibrated to divert flows in excess of sewage treatment plant capacity. A leaping weir may be used as a regulating device allowing typical dry weather sewage flow rates to fall into an interceptor sewer to the sewage treatment plant, but causing a major portion of higher flow rates to leap over the interceptor into the diversion outfall. Alternatively, an orifice may be sized to accept the sewage treatment plant design capacity and cause excess flow to accumulate above the orifice until it overtops a side overflow into the diversion outfall. Cso statistics may be confusing because the term may describe either the number of events or the number of relief structure locations at which such events may occur. A Cso event, as the term is used in American English, occurs when mixed sewage and stormwater are bypassed from a combined sewer system control section into a river, stream, lake, or ocean through a designed diversion outfall, but without treatment. Overflow frequency and duration varies both from system to system, and from outfall to outfall, within a single combined sewer system. Some Cso outfalls discharge infrequently, while others activate every time it rains. Csos should not be confused with sanitary sewer overflows. Sanitary sewer overflows are caused by sewer system obstructions, damage, or flows in excess of sewer capacity. Sanitary sewer overflows may occur at any low spot in the sewer system rather than at the Cso relief structures. Absence of a diversion outfall often causes sanitary sewer overflows to flood residential structures and/or flow over traveled road surfaces before reaching natural drainage channels. Sanitary sewer overflows may cause greater health risks and environmental damage than Csos if they occurred during dry weather when there is no precipitation runoff to dilute and flush away sewage pollutants. The stormwater component contributes a significant amount of pollutants to Cso. Each storm is different in the quantity and type of pollutants it contributes. For example, storms that occur in late summer, when it has not rained for a while, have the most pollutants. Pollutants like oil, grease, fecal coliform from pet and wildlife waste, and pesticides get flushed into the sewer system. In cold weather areas, pollutants from cars, people and animals also accumulate on hard surfaces and grass during the winter and then are flushed into the sewer systems during heavy spring rains. Csos in the United States equals about 772 communities in the United States have combined sewer systems, serving about 40 million people. Cso discharges during heavy storms can cause serious water pollution problems in these communities. Pollutants from CSO discharges can include bacteria and other pathogens, toxic chemicals, and debris. The U.S. Environmental Protection Agency issued a policy in 1994 requiring municipalities to make improvements to reduce or eliminate CSO-related pollution problems. It is managed by the National Pollutant Discharge Elimination System Permit Program. The policy defined water quality parameters for the safety of an ecosystem. It allowed for action that are site-specific to control CSOs in most practical way for community. It made sure the CSO control is not beyond a community unregistered trademark's budget, and allowed water quality parameters to be flexible, based upon the site-specific conditions. On January 1, 1997, the CSO control policy required all states to have a Eurocube 9 minimum control Eurocubed in place, which decreased the effects of sewage overflow through making small improvements in existing processes. In 2000, Congress amended the Clean Water Act to require the municipalities to comply with the EPA policy. Mitigation of CSOs. The United Kingdom Environment Agency identified unsatisfactory intermittent discharges and issued an urban wastewater treatment directive requiring action to limit pollution from combined sewer overflows. The Canadian Council of Ministers of the Environment adopted a Canada-wide strategy for the management of municipal wastewater effluent, including national standards to remove floating material from combined sewer overflows, prevent combined sewer overflows during dry weather, and prevent development or redevelopment from increasing frequency of combined sewer overflows. Municipalities in the United States have been undertaking projects to mitigate CSO since the 1990s. For example, prior to 1990, the quantity of untreated combined sewage discharged annually to lakes, rivers and streams in southeast Michigan was estimated at more than 30 billion U.S. gallons per year. In 2005, with nearly $1 billion of a planned $2.4 billion CSO investment put into operation, untreated discharges have been reduced by more than 20 billion U.S. gallons per year. This investment that has yielded a 67% reduction in CSO has included numerous sewer separation, Cso storage and treatment facilities and wastewater treatment plant improvements constructed by local and regional governments. Many other areas in the United States are undertaking similar projects. Cities like Pittsburgh, Seattle, Philadelphia, and New York are focusing on these projects partly because they are under federal consent decrees to solve their CSO issues. Both upfront penalties and stipulated penalties are utilized by the government to enforce CSO mitigating initiatives and the efficiency of their schedules. Municipalities' sewage departments, engineering and design firms, and environmental organizations offer different approaches to potential solutions. Sewer separation Some U.S. cities have undertaken sewer separation projects building a second piping system for all or part of the community. In many of these projects, cities have been able to separate only portions of their combined systems. High costs or physical limitations may preclude building a completely separate system. In 2011, Washington, D.C. separated its sewers in 4 small neighborhoods at a cost of $11 million. Cso Storage Another solution is to build a Cso storage facility, such as a tunnel that can store flow from many sewer connections. Because a tunnel can share capacity among several outfalls, it can reduce the total volume of storage that must be provided for a specific number of outfalls. Storage tunnels store combined sewage but do not treat it. When the storm is over, the flows are pumped out of the tunnel and sent to a wastewater treatment plant. One of the main concerns with Cso storage is the time it is stored before it is released. Without careful management of this time, the water in the Cso storage facility runs the risk of going septic. Washington, D.C. is building underground storage capacity as its primary strategy to address CSOs. As of 2011, the city is building a deep storage tunnel, adjacent to the Anacostia River, that will reduce overflows to the river by 98%, and 96% system-wide. The South Boston Cso Storage Tunnel is a similar project, completed in 2011. Expanding sewage treatment capacity Some cities have expanded their basic sewage treatment capacity to handle some or all of the Cso volume. In 2002, litigation forced the city of Toledo, Ohio to double its treatment capacity and build a storage basin in order to eliminate most overflows. The city also agreed to study ways to reduce stormwater flows into the sewer system. Retention basins Retention treatment basins or large concrete tanks that store and treat combined sewage are another solution. These underground structures can range in storage and treatment capacity from 2 million US gallons to 120 million US gallons of combined sewage. While each facility is unique, a typical facility operation is as follows. Flows from the overloaded sewers are pumped into a basin that is divided into compartments. The first flush compartment captures and stores flows with the highest level of pollutants from the first part of a storm. These pollutants include motor oil, sediment, road salt, and lawn chemicals that are picked up by the stormwater as it runs off roads and lawns. The flows from this compartment are stored and sent to the wastewater treatment plant when there is capacity in the Interceptor sewer after the storm. The second compartment is a treatment or flow-through compartment. The flows are disinfected by injecting sodium hypochlorite, or bleach, as they enter this compartment. It then takes about 20–30 minutes for the flows to move to the end of the compartment. During this time, bacteria are killed and large solid materials settle out. At the end of the compartment, any remaining sanitary trash is skimmed off the top and the treated flows are discharged into the river or lake. Screening and disinfection facilities Screening and disinfection facilities treat Cso without ever storing it. Called flow-through facilities, they use fine screens to remove solids and sanitary trash from the combined sewage. Flows are injected with sodium hypochlorite for disinfection and mixed as they travel through a series of fine screens to remove debris. The fine screens have openings that range in size from 4 to 6 mm, or a little less than a quarter inch. The flow is sent through the facility at a rate that provides enough time for the sodium hypochlorite to kill bacteria. All of the materials removed by the screens are then sent to the sewage treatment plant through the Interceptor sewer. Reducing stormwater flows Communities may implement low-impact development techniques to reduce flows of stormwater into the collection system. This includes constructing new and renovated streets, parking lots and sidewalks with interlocking stones, permeable paving and pervious concrete, installing green roofs on buildings, installing bioretention systems, also called rain gardens, in landscaped areas. Rainwater harvesting equipment collects runoff from building roofs during wet weather for irrigating landscapes and gardens during dry weather. Greywater collection and use on-site reduces sewage discharges at all times. Grey versus green infrastructure Cso mitigating initiatives that are solely composed of sewer system reconstruction are referred to as grey infrastructure, while techniques like permeable pavement and rainwater harvesting are referred to as green infrastructure. Conflict often occurs between a municipality's sewage authority and its environmentally active organizations between grey and green infrastructural plans. The 2004 EPA report to Congress on CSOs provides a review of available technologies to mitigate CSO impacts. New approaches Smart infrastructure Recent technological advances in sensing and control have enabled the implementation of real-time decision support systems for CSO mitigation. Through the use of Internet of Things technology and cloud computing, CSO events can now be mitigated by dynamically adjusting set points for movable gates, pump stations, and other actuated assets in sewers and stormwater management systems. Similar technology, called adaptive traffic control, is used to control the flow of vehicles through traffic lights. RTDSS systems take advantage of storm temporal and spatial variability as well as varying concentration times due to diverse land uses across the sewage to coordinate and optimize control assets. By maximizing storage and conveyance, RTDSS are able to minimize overflows using existing infrastructure. Successful implementations of RTDSS have been carried out throughout the United States and Europe. History Ancient sewers The earliest covered sewers uncovered by archaeologists are in the regularly planned cities of the Indus Valley Civilization. In ancient Rome, the Cloaca Maxima, considered a marvel of engineering, disgorged into the Tiber. During the Zhou dynasty in ancient China, sewers existed in various cities such as Lindsay. In medieval European cities, small natural waterways used for carrying off wastewater were eventually covered over and functioned as sewers. London's river fleet is such a system. Open drains along the centre of some streets were known as kennels. The 19th-century brick-vaulted Paris sewers serve as a tourist attraction nowadays. Most of these early sewers received significant amounts of draft animal dung in street runoff. But handling of human waste varied with location. Public latrines were built over the Cloaca Maxima, but chamber pot contents were prohibited from Paris sewers as recently as 1880. People wealthy enough to enjoy 19th-century flush toilets often had the political power to allow them to drain into public sewers. And the practice became the norm as indoor plumbing became more common. Industrial Revolution As a product of the Industrial Revolution, many cities in Europe and North America grew in the 19th century, frequently leading to crowding and increasing concerns about public health. As part of a trend of municipal sanitation programs in the late 19th and 20th centuries, many cities constructed extensive sewer systems to help control outbreaks of disease such as typhoid and cholera. As Britain was the first country to industrialize, it was also the first to experience the disastrous consequences of major urbanization and was the first to construct a sewerage system as we know it today to mitigate the resultant unsanitary conditions. During the early 19th century, the River Thames was effectively an open sewer, leading to frequent outbreaks of cholera epidemics. These were caused by enterotoxin-producing strains of the bacterium Vibrio cholerae. Proposals to upgrade the sewerage system had been made during 1856, but were neglected due to lack of funds. However, after the Great Stink of 1858, Parliament realized the urgency of the problem and resolved to create a sewerage system. Joseph Bazalgette, a civil engineer and chief engineer of the Metropolitan Board of Works, was given responsibility for the work. He designed an extensive underground sewerage system that diverted waste to the Thames estuary, downstream of the main centre of population. 6 main interceptor sewers, totaling almost 135 miles in length, were constructed, some incorporating stretches of London's lost rivers. 3 of these sewers were north of the river, the southernmost, low-level one being incorporated in the Thames embankment. The embankment also allowed new roads, new public gardens, and the Circle Line of the London Underground. The intercepting sewers, constructed between 1859 and 1865, were fed by 450 miles of main sewers that, in turn, conveyed the contents of some 13,000 miles of smaller local sewers. Construction of the Interceptor system required 318 million bricks, 2.7 million cubic meters of excavated earth and 670,000 cubic meters of concrete. Gravity allowed the sewage to flow eastwards, but in places such as Chelsea, Deptford and Abbey Mills, pumping stations were built to raise the water and provide sufficient flow. Sewers north of the Thames feed into the Northern Outfall Sewer, which fed into a major treatment works at Beckton. South of the river, the Southern Outfall Sewer extended to a similar facility at Crossness. With only minor modifications, Bazalgette's engineering achievement remains the basis for sewerage design up into the present day. Another significant engineer of the period was William Lindley, who, in 1863, began work on the construction of a sewerage system for the rapidly growing city of Frankfurt am Main. 20 years after the system's completion, the death rate from typhoid had fallen from 80 to 10 per 100,000 inhabitants. Initially these systems discharged sewage directly to surface waters without treatment. As pollution of water bodies became a concern, cities added sewage treatment plants to their systems. Most cities in the Western world added more expensive systems for sewage treatment in the early 20th century, after scientists at the University of Manchester discovered the sewage treatment process of activated sludge in 1912. During the half-century around 1900, These public health interventions succeeded in drastically reducing the incidence of waterborne diseases among the urban population, and were an important cause in the increases of life expectancy experienced at the time. Society and culture. The image of the sewer recurs in European culture as they were often used as hiding places or routes of escape by the scorned or the hunted, including partisans and resistance fighters in World War II. Fighting erupted in the sewers during the Battle of Stalingrad. The only survivors from the Warsaw Uprising and Warsaw Ghetto made their final escape through city sewers. Some have commented that the engravings of imaginary prisons by Piranesi were inspired by the Cloaca Maxima, one of the world's earliest sewers. Regulations United Kingdom. There is in the UK a legal difference between a storm sewer and a surface water sewer. You do not have a right of connection to a storm sewer under Section 106 of the Water Industry Act. These are normally the pipeline that discharges to a watercourse, downstream of a combined sewer overflow. It takes the excess flow from a combined sewer. A surface water sewer conveys rainwater. Legally you have a right of connection for your rainwater to this public sewer. A public stormwater sewer can discharge to a public surface water, but not the other way around, without a legal change in sewer status by the water company. And fiction. The theme of traveling through, hiding, or even residing in combined sewers is a common plot device in media. Famous examples of sewer dwelling are the Teenage Mutant Ninja Turtles, Stephen King's It, Les Miserables, The Third Man, Lady Hawk, Mimic, The Phantom of the Opera, Beauty and the Beast, and Jet Set Radio Future. The Todd Strasser novel Y2K9, The Dog Who Saved the World is centered around a dog thwarting terroristic threats to electronically sabotage American sewage treatment plants. Sewer alligators. A well-known urban legend, the sewer alligator, is that of giant alligators or crocodiles residing in combined sewers, especially of major metropolitan areas. Two public sculptures in New York depict an alligator dragging a hapless victim into a manhole. Alligators have been known to get into combined storm sewers in the southeastern United States. Closed-circuit television by a sewer repair company captured an alligator in a combined storm sewer on tape. See also, sanitary sewer overflow, storm drain. References. External links, US EPA Euro combined sewer overflows.